All right, let's talk about the last section in Chapter 7, 7.5, solving trigonometric equations. Now, you guys have seen a bunch of these already, but every single one of them you've ever seen, the bounds have been between, for theta, have been between 0 and 2 pi, just like this. They've always been like that. Now we're going to start saying, well, what happens if we start messing around with the bounds that we give you? Now, how do you do it? Now, what does it look like? What happens if there are no bounds? What does that kind of an answer look like? Those are the kinds of questions we're going to look at. So there are a ton of examples in this, and you can look at the video length and see that there are indeed a ton of examples in this. So we're just going to do these rapid fire. Some of these are quick, some of these aren't quite so quick. So this one says, find all possible exact solutions for the equation cosine theta equals 1/2 on 0 to pi over 2. Now we say all possible exact solutions. That means please leave the root 2's in there. That means do not put in decimals. So let's find all possible exact solutions for the equation cosine theta on 0 to pi over 2. So we're in quadrant 1. So where is cosine of theta equal to 1 over 2 in quadrant 1? Pi over 3. That's the only thing you can plug into cosine in quadrant 1 to get out 1/2. Cosine being x. You're done. That's it. It's just in quadrant 1. There are no other values. Let's look. The next one asks us to find all possible exact solutions for the equation cosine theta equals 1/2 on pi over 2 to pi. So pi over 2 to pi, of course, is q2, whereas cosine of theta, x, equal to positive 1/2 in quadrant 2. There are no places, of course. So theta, okay, you could say no solution, or you could say theta equals the empty set, but I would just say no solution. Because there is nothing that is a positive 1/2 in quadrant 2 for the x on your unit circle. That doesn't exist. So there's no solution. So don't let me trick you with things like this. Next, examples 3 and 4. Example 3 says, find all possible exact solutions for the equation cosine theta equals 1/2 on 0 to 2 pi. So this is what you're used to. Notice that in this example you also include 2 pi again. So 0 and 2 pi, that same point. After 0 revolutions and after 1 revolution, they're both included. It doesn't matter in this case. So where is cosine of theta equal to 1/2 on the entire unit circle? Well, there'll be 2 places. The first place that it equals is at pi over 3. Okay, and then the next place it's going to equal will be all the way down at 5 pi over 3. And just look at your unit circle as we go through this. If you don't have a unit circle out when I'm going over this, you definitely should. But you'll notice that the x-coordinate for pi over 3 is 1/2, and the x-coordinate for 5 pi over 3 is also 1/2. Now, this one down here asks one more time. It says, okay, same question except on 0 to 4 pi. So instead of going to 2 pi, you go to 4 pi. Oh, okay. So we're just going to go around one more revolution. So it's obviously going to have the same 2 solutions. So 2 of the solutions are going to be pi over 3 and 5 pi over 3. But what if you keep spinning? Well, the other 2 solutions to this one are going to look like, well, each one of these plus 2 pi, plus an additional revolution. So you know, I'm talking about example 4 down here, but you know that you have a unit circle like this, okay? The question is, you know that your points are here and here. So the first time, you only went around that far, pi over 3, and 5 pi over 3. That was the first 2 ones. But now the question is what happens if you come around this far, and then you go around 2 pi? Well, you're just back to here again, right? So it's that same point. And then the other question is, well, okay, what if you go around this far, that is 5 pi over 3, and then, in orange, we go around another 2 pi? Well, we're back to the same point, aren't we? And we are allowing, this means 2 revolutions. 0 to 4 pi means 2 revolutions. So we're going to have the 2 answers, and then we're going to add 2 pi to each of them is what we're going to do. So we're going to add 2 pi to each of those numbers. And we're going to figure out up here, again, we're doing example 4 in this space up here, and we're going to figure out what pi over 3 plus 2 pi is. So that's pi over 3 plus 6 pi over 3, which is 7 pi over 3. So that must be an answer. 7 pi over 3 must be an answer. So we're going to write that. So 7 pi over 3 is an answer. And then the other one, we're going to take for the 5 pi over 3, and we're going to go around an additional revolution. And we're going to see that this is still 6 pi over 3, that's just 11 pi over 3. So 11 pi over 3. So 11 pi over 3 must be an answer. And that's going to end it for us. That is all 4 of our answers. So the blue ones here are in 1 revolution. These orange ones here are the ones that show up when you spin around again. But all that they are is just take the first 2 and add 2 pi to each of them, because that's how you spin around the whole revolution again. That is their coterminal angles. And that's it to that. So let's just take that to its logical conclusion. Solve cosine theta equals 1/2. On what? Is there a domain restriction up there? No, there isn't. So you can spin around positively as many times as you want, negatively as many times as you want. Any cosine you want. Well, you know what the solutions are going to be if you solve it on 0 to 2 pi. You know that the two solutions were going to be pi over 3, okay, and giant comma, I'm going to leave some space, I got to put some stuff there, and 5 pi over 3. Those are the two just solved normally, all right? And then I'm going to come all the way over here. I've got to write some extra stuff here. So here's how this is going to end up working. What we need to do is just add those 2 pi revolutions over and over and over. The last time we got the other ones by adding in, I guess I don't need that yet, by adding in 2 pi. So we're going to do that. We're going to add in 2 pi. We're going to add in 2 pi to both of them. But that only handles me for 1 extra positive, because it's plus, 1 extra positive revolution. So the question is how do I tell it to spin around as many times as it wants to in either direction? How might I go about doing that? And the simple answer to that is we just add in a k to both of these, okay? And then we say such that, and then we tell, this is set builder notation, we say such that k is an integer. And that's the answer to your problem. So k is an integer. What's an integer? It's 0, 1, 2, 3, 4, 5. So if k is 0, then we're adding 0, and we just get the 2 normal answers. If k is 1, then we're adding 2 pi times 1. We're adding 2 pi. If k is 2, then we're adding 4 pi. That is, we're going around twice. If k is 3, we're going around 3 times. Integers also include the negative numbers, so that's going around negative as well. So if it's -1, then we're subtracting 2 pi from pi over 3. That's fine. You went around the quote-unquote wrong way. You went around clockwise. You went around negatively. This is going to handle everything. So to just solve these things in general, it's always going to work out like this. You just find the normal answers, and then you slap them in a set builder notation thing like this. You add 2 pi k to each one of them, and you tell me such that, that's what that means, such that k is an integer. K is an integer, and you're done. That's it. Every time you want to solve something like this, it's the same way. Find it as though you were restricted between 0 and 2 pi. Find it just like that. And then add 2 pi k to each one of them and tell me that k is an integer. K is a dummy variable, by the way, here. You could call these both j's or q's or t's if you felt like it. As long as they're all called the same thing, it doesn't matter. That's how you solve it. And all that this means is just go around k times. Go around k times, and you're counting k 1, 2, 3, 4, 5. So you can't do like a half revolution on accident. You can only go around whole multiples of positive or negative natural numbers. And you may want to write that down in your notes. If you missed what I said, just rewind. It's the power of video. Let's go look at the next several. But once you get this down, the rest of these just fall in line real quick. So let's zip through them. So we're going to do 2 of these real quick. Solve the sine of theta equals √3/2. So pause the video and give it a shot. Use what we just learned to see if you can do it. Go ahead. So hopefully you actually did that. And you remember that it's just theta equals, and remember, what you're going to do is you're going to solve root 3 over 2 normally. So just look on the unit circle in 0 to 2 pi. Root 3 over 2 shows up in the y component 2 places, pi over 3 and 2 pi over 3. So you're going to do pi over 3, and then there is no domain restriction. So add 2 pi k, okay, comma, the other one was 2 pi over 3. So add on those as many times as you want, such that, and then tell me that k is an integer. An end. That's it. That's the answer. So it's solve it normally, add 2 pi k onto both of them, and tell me that k is an integer. The next one down here says solve sine theta equals cosine theta on 0 to 2 pi. That is saying, in one revolution of the unit circle, where are sine and cosine the same? 2 places, pi over 4 and 5 pi over 4. And it's just on one revolution, so that's all you have to tell me. So 2 places, pi over 4, they're the same, and 5 pi over 4, they're both negative there. Okay, at pi over 4, they're both root 2 over 2. At 5 pi over 4, they're both negative root 2 over 2. Okay, let's look at the next one. And you'll notice that the next one says solve sine theta equals cosine theta. But this time there is no domain restriction. So how do you write it? Well, we've got the solution on 0 to 2 pi up here, already done. So let's look now, and let's do this one. So this is theta equals, well, it's the same answer, except each time you write your answer, since there is no domain restriction, you have to add plus 2 pi k. That is as many revolutions as you want. And the other one, 5 pi over 4. Okay, plus as many revolutions as you want. That's what that means. Such that k is an integer. That's it. That's how you solve it with no domain restrictions. You just put it in there, plus 2 pi k. Or 2k pi if you prefer. It doesn't matter which order you put it in. It's all the same thing. You could put k2 pi on it if you felt like it. But like, why would you do that? Don't be dumb. That's how to do those. So you just take what it is on 0 to 2 pi, one revolution, and just add this extra junk in. And you're done. Okay? Let's look at yet another one. So this one, we want to solve cosine theta minus sine theta equals 0. So this question is asking, where can we take sine theta and take it away from cosine theta, and there's nothing left? Wait a tick. If I just add sine theta to both sides, isn't this just cosine theta equals sine theta? And isn't there no domain restriction? So it's literally the exact same answer as last time? Think smarter, not harder, right, guys? If you can solve this thing and get it to look like something you've already done, it's the same answer. So if you want to look back in your notes. It's literally the same answer as the last thing. It's the same problem. Asking where they're equal and asking where you can subtract one from the other and get nothing left, it's the same thing. Because any number minus itself is 0. So if they're the same thing, then they're the same thing, and subtracting a number from itself gives you 0. That should make sense. I'm not even going to dignify this with writing the answer down again. If you want to write it down again, write it down again. If you want to write this down, though, it's just same as last. Moving on. These are both really fun. Solve cosecant theta equals negative 2, and solve cosine 2 theta equals 1. Cosecant of theta equaling to negative 2. There is no domain restriction. You can, of course, just look this up on your sheet, or you can do a little bit of math. Cosecant is 1 over sine, so we're saying where is 1 over sine theta equal to negative 2, which means we're saying where is sine theta over 1 equal to negative 1/2. And we know that sine of theta is equal to negative 1/2 at 2 places. It's equal to negative 1/2 at 7 pi over 6. Okay, but there's no domain restriction, so you have to add in 2k pi, or 2 pi k, whatever you want to call it. It doesn't matter. And 7 pi over 6 was one of them. The other one is 11 pi over 6, plus your 2k pi. Wow, that's bad. Plus your 2k pi, such that, and then tell me that your k is a integer, like that. That's your answer. That's it. We solved it. Good job. You could look, of course, on your sheet and find these two parts really easy. Add in your 2k pi's because there is no domain restriction. Then the next thing says solve cosine of 2 theta equals 1. Okay, with no domain restriction. So you're going to have this garbage in the answer for sure. You know that for a fact. But also, how do we go about doing this? Well, I see cosine 2 theta, and I think back to the last couple sections we did, and I know that there are some identities that we can use. One of them in particular says that cosine of 2 theta is just equal to 2 cosine squared theta minus 1. So let's write that down. Let's write that down and remember that. So we know that, let's write it here. Cosine of 2 theta is equal to 2 cosine squared theta minus 1. So I'm just going to write this equation a little bit differently then. So instead of writing this, I'm going to write this. So I'm going to write 2 cosine squared theta minus 1 equals 1. I'm then going to add 1 to both sides and divide by 2, and this is going to turn into cosine squared theta equals, well, 1. Because I add 1 to that side, I get 2 cosine squared theta minus 1 equal, rather, 2 cosine squared theta equals 2. If I add 1 to both sides, divide by 2, I get 1. And then I just take the square root of both sides. So the question is asking, where is the cosine of theta equal to plus or minus the square root of 1, or plus or minus 1? So where does the cosine of theta equal plus or minus 1? Well, that's pretty easy. So the cosine of theta equals plus or minus 1 on a normal, remember there is no domain restriction, so on a normal thing, cosine of theta is going to be plus or minus 1 at either 0 or pi. It's going to be plus 1 at 0, and it's going to be negative 1 at pi. So then our answer, in orange here, is going to be theta equals, well, 0 plus 2 pi k. Write it however you want to, guys, like this or like this, doesn't matter. It's up to you. And pi plus 2 pi k, such that k is an integer. Okay, so we just used a little identity here to make this really easy. Awesome. But that's going to be the two places that those are going to be equal. All right, and that's all of the places that it shows up. If you wanted to write this right here as just 2 pi k, you could, but I think putting in the 0 makes it a little bit more obvious. Let's look at the next one. 2 times the quantity tangent theta plus 3 equals 5 plus the tangent of theta on just one revolution of the unit circle. Okay, no big deal. So let's write this down, and let's simplify it down to something simple. Let's get all the tangent terms on one side, all the constant terms on the other, and just see what this turns into. So 2 tangent theta plus 3 equals 5 plus tangent theta, okay? And we're going to divide this in half. So let's distribute in this 2 over here real easy. So we'll get 2 tangent theta plus 6 equals 5 plus tangent theta. Okay. I'm going to, let's see here, subtract the 6 over. And I'm going to subtract this tangent over, so I'm going to do it like that. So I'm going to get 2 tangent theta minus tangent theta equals 5 minus 6. So then this is tangent theta equals negative 1. That's the question. Where does tangent theta equal negative 1? Well, tangent theta is going to be 1. Remember, it's the question is asking tangent theta equals 1 is when they're the same. The only thing that's different here is their sign. So tangent theta equals negative 1 is saying, when do you divide sine by cosine, the y by the x, and you get a negative out? Well, the only way you're going to do that is if the values are the same, but the signs are different. And that happens at 3 pi over 4 and 7 pi over 4. So that's your answer. That happens at 3 pi over 4 and 7 pi over 4. There's no domain restriction. There is a domain restriction on it, rather. So that's the whole answer. However, if there were no domain restriction, you would just add 2 pi k to each one of them and tell me that k is an integer. So that looks hard, but you just simplify it down. Turns out to be pretty easy. So we're going to solve cosine squared plus 3 cosine theta minus 1 equals 0. So this may look really difficult to you, and you may be thinking, well, maybe I need to use a reduction formula on this or something. Maybe I need to use Pythagorean identity on that. Maybe I need to do something. No. We're going to use everything we've ever learned about quadratics, because this is a quadratic in cosine theta. What I mean by that is your variable is cosine theta. So look here. If instead of cosine theta, I said let x be cosine theta. Okay? Let x be cosine theta. So instead of writing cosine thetas, I'm going to write x. Then what this turns into is instead of cosine theta squared, this is x squared. Plus 3 times, instead of cosine theta, we're going to write x. Minus 1 equals 0. If we can solve this using the quadratic formula, then we can solve this using the quadratic formula too. And that's exactly what we're going to do. So we're just going to solve that using the quadratic formula. So the quadratic formula says x equals a bunch of stuff. But remember, we don't have the variable x, we have the variable cosine theta. So we're going to solve cosine theta equals a bunch of stuff. What bunch of stuff? Well, minus b plus or minus the square root of b squared minus 4 times a, which is the number in front of this, which is 1, times c, which is this number, which is negative 1, all over 2 times the number in front of a, which is 1. So instead of having a x over here, we have a cosine theta over here. Otherwise, it's just a polynomial. It's solved exactly the same way. So what does this reduce down to? Well, this is minus 3 plus or minus, let's see here. What's underneath the radicand here? What's this? What is this? That's 9 plus 4, apparently. That's 9 plus right there, 4. 9 plus 4 is 13. So like that over 2. Okay? So this is one of those weird ones where it shows up. So the question is then, all right, well, let's look at both of these values and figure out what's going on here. Because we have then, therefore we can say, I'll do it in a different color, the cosine of theta equals minus 3 plus or minus the square root of 13 over 2. Well, that's not on our unit circle pretty clearly. So in order to solve this one, we're going to have to use an inverse. Easy enough. Therefore, theta is just going to be, and now you've got to think about this. It's going to be the arc cosine of one or both of these, but remember, the arc cosine can only take in values between negative 1 and 1. So shove both of these into a calculator and figure out which one of them, if either, gives you negative 1 or 1. If neither one of them gives you negative 1 or 1, neither the positive version or the negative version gives you a number between negative 1 and 1, that is, gives you a proper fraction, that is, gives you a decimal that is positive or negative 0 point something, then you can't use either of them. But if one of them works and the other one doesn't, throw out the one that doesn't. So we're going to think about this. Notice I haven't drawn the plus or minus yet. We're going to think about this, and we're going to figure out which one we can throw in and throw out. So we're going to plug in negative 3 plus root 13 over 2 into a calculator. And we're going to plug in negative 3 minus root 13 over 2 into a calculator and figure out which one works. It's probably going to be the plus, and I'll tell you why I'm guessing that in just a second. So take a minute, plug them in, and see what you get. So like I said, the one that we're going to end up keeping is the plus. Okay, if you do the plus version, it's 0.3 something. If you do the minus version, it's negative 3 point something, and you cannot plug a number greater than 1 or less than negative 1 into an arc cosine function. So you cannot take the minus version. So your theta is going to be the arc cosine of negative 3 plus root 13 over 2. Now, how did I know this was going to be the one that worked? Well, this is a negative number, and I'm adding to it a positive number. So it's going to take me closer towards being inside my bounds. If I already have a negative number and then I then subtract a positive number, I'm going to get even further away from my bounds, which is the logic that I used to know which one was going to be the answer without even looking at it. However, if you just type in the arc cosine of this into a calculator, you'll get an approximate answer, I guess, and we can talk about it. And so if you run this thing through a calculator, you get about 1.26 or so. This is about 1.26, okay? And if you want all of the answers, you just add 2k pi to it and tell me that k is in the integers. And so that'll give you all of the different things that you can add to this and throw in. Now, the problem with doing this exactly like this, if you want the exact answer, is that this is technically wrong. Because you're using an approximation here, as you rotate around, there's a chance, based on how bad this approximation was, that your answer just gets more and more wrong the more and more times you go around. And that may be confusing, but think about it this way. It's probably better to add the 2k pi to this. But honestly, usually, and here's the whole point, if you're using arc cosine and arc sine, we just keep it to the one answer. There's more than one answer. But since we had to use arc cosine to figure it out, and because of that restriction we had to do, let's not get into anything more complicated. It's 1.26. Move on with life. All right? Let's look at the last one here, which we're definitely going to need more space for. So we're asked to solve sine squared theta plus 2 sine theta minus 3 equals 0. So go ahead and give it a shot. You know how we just did the last one. Pause the video. Give it a shot. It's why I did one that was almost identical. See what you can find. Now the numbers are slightly different, of course. So we will have to do the quadratic formula again. So let's see what we can do. So this time it's in sine theta. So sine theta equals minus b plus or minus the square root of b squared. I'm just going to go ahead and write it. Minus 4 times a times c all over 2 times a. A is 1. It's that number right there. Go ahead and solve this really quickly. So this is minus 2 plus or minus the square root of. That's 4 plus 12 is 16. Oh, this is going to work out a lot better for me already, I can tell. Over 2. So this is going to be negative 2 plus or minus 4 over 2. Which is going to be, well, that's the same thing as, I guess, if you divide the 2 into both of them, that's negative 1 plus or minus 2, which is the two different answers. Negative 1 plus 2. Negative 1 plus 2 being 1. And negative 1 minus 2 being 3. So 1 and 3 are the two different answers. So the question is, where is sine of theta 1? Where is sine of theta 3? Those are the two questions that you're asking. It's pretty easy. The questions is now asking, where is sine of theta equal to 1? And where is sine of theta equal to 3? That's the two questions. Well, sine of theta is equal to 1. Look, there is no domain restriction. Sine of theta is equal to 1 at only one place, pi over 2. So theta equals pi over 2. But there's no domain restrictions, so it's plus 2k pi, such that k is an integer. Where is sine of theta equal to 3? You're on the unit circle. Sine of theta only ever gets to 1. It never gets any bigger. So there's no solution there. So the entire solution is just that part. So pi over 2 plus 2k pi such that k is an integer. And that's it. You're done. This is the hardest kind of problems that I can give you. I guess the previous one is even harder. So if it works out real nice so that you can do normal trig stuff on it, like this one did, go ahead. If it works out where the last one did, where it's definitely not on the unit circle, then just do it the way you're going to do it, using the arc cosine or the arc sine, and you're done with that. But just remember, if you see something like this one, where it's just a polynomial, you can just use the quadratic formula. And yes, by the way, you could have factored this as sine theta minus 1 times sine theta minus 3 if you wanted to. You could have done that if you wanted to. Sine theta plus 3, rather. This is a minus 3 over here. It changes exactly nothing, in case you're wondering. It could still never be negative 3. But you could have just factored this as sine theta minus 1 times sine theta plus 3 equals 0. And then set each part equal to 0 and solve, and you would have got these two problems the same way. If you wanted to do it that way, factor it whatever you want to. The game was what two numbers multiply together to give you negative 3 that add together to give you 2. And clearly it's, well, what we got. So play the game however you want to, but that is the end of not only the section, but the chapter. So I'll see you again in the final chapter, chapter 8, where we'll go over the law of sines, the law of cosines, a whole bunch of other stuff, and even get to vectors. So I'll see you then.